Today, we're going to put our vertical circles in a different light. So we talked about vertical circles. Where am I? I talked about vertical circles using the string. So when we stop this at the bottom of my circle, then the tension and weight are in opposite directions. And since we always put the direction of the acceleration as positive, and we know the circular acceleration is towards the middle, our sum of the forces becomes T minus W. And we know that the tension is equal to the weight plus mv squared over r, because the string has two jobs. Job number one, to hold up the wiffle ball, and job number two, to keep it going in a circle. So it does those two jobs mathematically here. W plus mv squared equals the tension. At the top of the circle, it's a different story, because at the top of the circle, we have both, if I stop this at the top of the circle, we have both the tension and the weight pulling down. So that tension plus W is equal to mv squared over r. And we talked about this being a limiting situation, so that if I rotate this thing at too slow of a speed, it falls out of the circular path and the tension becomes zero. Well, when you ride a roller coaster or any amusement park ride that has a loop-de-loop, or any type of hill for that matter, but today we're going to focus on the loop-de-loop, we get the exact same situation, except in place of T, we substitute the idea of the normal force. So the normal force with respect to the roller coaster is the same thing as the tension with respect to the wiffle ball. So down comes this car, down the hill, down the hill, down the hill, down the hill, down the hill. And now it's sitting right here at the bottom of this hill. Well, the force diagram of anybody sitting in this car has the normal force pushing upwards and the weight going downwards. So any place we see tension, when we were talking about the string, we now see normal force. Now, a super important thing here for this normal force, it's the force perpendicular upward from a surface. Now, in our case, in this particular case, the normal force provides the weight. The normal force is the apparent weight. That is how heavy you think you feel. Now let's think about this. If the cart is just sitting here and there's a person inside the cart, this speed goes to zero and the normal force is equal to the weight of the car. That is what that says. But if the cart is traveling fast as we come down the incline, coming, now all of a sudden, this thing's going fast. Basically, the person is being pushed down into their car. So the normal force is going to get bigger by an amount equal to mv squared over r. So down at the bottom here, your apparent weight, Fn, I'm going to write this in blue. Down here at the bottom, Fn is greater than your actual weight. This is your actual weight. That never changes no matter what's happening as long as you're at or near the surface of the earth. Fn is bigger than W by an amount equal to mv squared over r. So you feel lighter than you actually are. I'm sorry, you feel heavier than you actually are by an amount equal to mv squared over r. So, you know, when you travel down this loop-de-loop, or when you travel down this hill, You're getting pushed back into your car. You feel heavy, 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 heavy. And now what happens when we go on the loop-de-loop? Now we're upside down. And now your chair is actually pushing you downwards. And as odd as that sounds, the normal force here is now in the same direction as the weight. So the weight and the normal force are combining to keep you in the circle. And there's two ways for us to look at that mathematics. Number one is through the lens of the apparent weight. So Fn is equal to mv squared over r minus w. So first and foremost here, in order for you to feel any weight, Fn has to be greater than 0, which means mv squared over r must be bigger than w. So you have to go a minimum speed in order for you to feel any weight. That v has to get big enough so mv squared over r is bigger than the weight. The other way for us to look at that is through the lens of what happens if you go slower than you're supposed to. Remember, in order to stay in the circle, the left side has to be equal to the right side. Now, W can't change, so we have a limiting factor here again. The cart, so the roller coaster, could lose contact with the track. What would that mean? That would mean the normal force was equal to 0 because the seat wouldn't be pushing you down anymore because the car would be falling with you. So the roller coaster can lose contact with the track. Well, that happens when the normal force is equal to 0. Well, if the normal force is equal to 0, then W equals mv squared over r. In which case, that V is the minimum V. That's our V minimum. Just like we had a V minimum with our wiffle ball, right? If I twirl this thing around the circle, too slowly, it falls out of the circle. So now if W is equal to m times g, and that equals V min divided by r, then g times r square rooted is my minimum velocity that this thing would need in order to stay in the circle. So how does that play out? Well, we could show that with these balls. So if I have this ball and I start it super high, it's going to have a speed greater than this minimum speed, so it will make it all the way around the circle. Again, the equivalent to that is I'm twisting this ball fast enough, it goes all the way around the circle. If this ball rolls down and it's going fast enough, it'll go all the way around the circle and come off the end. Now, of course, as I lower this down, it's not going to be going as fast around the circle. And we'll get to the reason for that in a couple weeks. But when this ball comes down, right here, it experiences a normal force that's greater than its weight. Up here, it experiences a normal force that's less than its weight. And in fact, if it's not going fast enough, it will lose contact with the with the track altogether and won't experience a normal force at all. So watch what happens when I put this thing down too low. You can see that the ball does not even make its way around the circle. And again, I could, oops. So it goes up here, it loses contact. Why? Because its speed is not equal to that minimum. So we can find a spot on this ramp where it just barely makes it over. And we just keep getting, yeah, we're almost there. This is the spot where it just barely makes it through. And the math that's associated with that is the same as the math that's associated with the wiffle ball on a string.